continuing on with what was covered in Class 20, we're going to talk about other CAM acceleration functions that we could try to use. Now, going back through and taking a look at some of the other models right here, you could see that the acceleration was infinite in this first novice one right here. But you also had a steep jump right here in the junior. It was in the sophomore where we took the sine wave function and then worked backwards and forwards to get this shape right here. And that shape was related to this CAM. So now it really depends on what kind of other types of things that we want to accomplish here. So a constant acceleration, you could think of that as being just a step function, right? Right here, right? So that we have, here's an acceleration and here's an acceleration, so in between there. And you can see that the consequences are that the jerk is infinite. Well, we could also try for a trapezoid, right? So we'll try to instead smooth out the lines of the, and so we'll make a smooth line and make a slope to go from one spot to the next, right? Instead of make it infinite, but that still results in a step function, and this is not continuous. So what we could do instead of trying to make a sudden jump or a smooth jump is now to try to take part of a sine wave to smooth out that jump. And what we end up finding when we do that is, let's see, looking. We combine the two, and what we end up, we get a what we call the modified trapezoidal acceleration. But this isn't like the greatest thing either. So we do have some downsides to that. We could also try to do a modified sinusoidal right here, right? So that we take a quarter of a sine wave, we take a longer sine wave, and then take another quarter of a sine wave, so that we could try to make these transitions right here kind of like a smoother thing. And then also they have the sine, constant, cosine type of acceleration, where they go SCCA, where they are taking like different zones about the thing and adding them together to be able to generate the piece that they want. Yeah, I'm not explaining that as well as I possibly could. It's almost better to like see them superimposed on top of each other. So here is one where they've plotted various different CAM followers, SVAJ diagrams, in just a portion of them. So here's a cycloid, modified sine, modified trapezoidal, and simple harmonic. And so you could kind of see what the J up here. Really it's the jerk that we're concerned about, right? That we have. So you can kind of see they're all combined to each other. And we do have a jump right here, and there's a jump right here, jumps into there, but then this one's bad because it's infinite right there. So it would be nice if we could make this continuous, or it'd be at least not infinite, right? But it would be good if we could make it continuous. But you can see that this can't be, the jerk can't be continuous if this is not continuous, right? But even still, we're having difficulty doing it. So here are some of those things, this example being placed into this, right? Where I call this example 1, but I think it should be example 4. Yes, I believe so. This should be example 4, where we have this raise, fall, raise, right? So we have like a senior CAM design and its combined functions for a better CAM design. We can also use polynomials, right? So we can have either a 3, 4, 5 polynomial or a 4, 5, 6, 7 polynomial, and those refer to what the coefficients are right in here. And these parameters right here, I believe they're developed for us to try to smooth these things out. There are coefficients that stab in front, and yeah, sure enough, they've actually been solved, and we get parameters for them, and yes, for the 4, 5, 6, 7, and we're getting numbers. So that ends up being, I think, example 8.6. Where we work through those. No, that's not true. So as you look through there, you could find, okay, so no, example 8.8 is where we find the symmetric rise fall of a single dwell case. Right, that's going to be what this example has done. And so these are and working through these examples. Here is what they end up looking like, and I've accidentally cut this off, but you could kind of see that this right here is not continuous. At least it doesn't jump, right? At least these don't jump as part of this. And so here's some like comparisons of all of these various strategies of trying to get accelerations to not be infinite, and for jerks to not be infinite as well for these various shapes. And here's the book's interpretation of the of these shapes. So that's what I have for this portion of the lecture. Which, was it worthwhile? I don't know. Maybe.